Hey guys, wish you all a very good evening. Hi Tim. Can you just confirm if you can hear my voice and read my screen? 6018, perfect. Thank you for that. Guys, is it too noisy? Actually, the thing is, I'm kind of traveling and there is family around, so it might be a bit noisy. Just want to know, is this noisy or is it, am I audible? Is there a lot of noise or it's okay? Just wanted to understand that. Anyone? Or is it so noisy that you're not able to get my question? What's happening, guys? Am I audible? Can you please confirm? Audible occasional noise, but not so problematic as of now. Okay, perfect, guys. So please, if it gets too noisy, right, please let me know. I'll see if I can do something about it. Right now, I don't want to do anything, but if it does get noisy, please let me know. Okay. It's important to make sure this class goes well because it's kind of an important topic. And you know, it's like for the first time we're going to learn an architecture which solves a fundamental problem with neural networks. And pretty much all the successes that you see with large language models is dependent on this idea. So I just want to make sure I convey this idea perfectly. So yeah, if it gets noisy, please let me know. Otherwise, how's it going, guys? Wednesday of the week. How is everything? Middle of the week. I guess it's a bit tiring for everyone to come and attend a class in on Wednesday. But hopefully, the class is a bit exciting since we're going to solve an interesting problem. So yeah, that's the trade-off. Cool. As usual, we will start class in a couple of minutes. Just waiting for more people to join in. As more people join in, we can go ahead. Hey, good evening, Ajay. Good evening, Arun. Glad to see you join in. What's up? I hope you guys are doing well. So let's just wait for a few more people to join in and we can get started. By the way, a lot of openings right now are going to be available because of the success of ChatGPT. So knowing how these things are done is kind of helpful. So yeah, at least from a job point of view, I guess for a while people are going to be really excited about NLP applications to industry problems. So yeah. And it's generally very interesting to see how people take a problem in neural networks and then solve the problem by modifying the architecture. Like it's kind of rare. So at least in computer vision, architectural changes aren't that many, right? I mean, at max, the last big architectural change, I suppose, was when GANs came in. So if you guys are aware of style GAN, that is one place where a huge change came in. But apart from that, not really much architectural changes. Ajay's question is, can we also discuss how to productionize deep learning models? Definitely, Ajay. So we could take this up as a question in the this thing at the end of the lecture. I would love to talk about that. Productionize. Hey, hi, good evening, Deepat. Glad you could join in. So generally, productionizing deep learning models essentially just requires you to understand the concept of transfer learning, right? If you're solid with the concept of transfer learning, if you are able to understand what is the problem that my original network solves, how this network will fit into a new architecture to solve a different problem, if you're able to figure that out, right? If you're able to formulate that, I believe it's possible to solve a lot of problems because honestly, by reading so many papers in neural networks and computer vision literature, my feeling is the innovation required is just at the architectural stage and at the overview stage, like defining the task. If you have a well-defined task, right, and you are aware of the concept of transfer learning, it generally becomes easy to handle these problems. So my 2 cents on that is this. If you want to discuss this further, we could definitely discuss this. Amit says he's still not able to access the project. So Amit, it turns out that the problem is on our side. There is a problem with the definition of that. So it did not pass a check, the current case study. It's sort of, there is an issue with the problem statement itself. We're fixing that. So it will take a little bit of time. I'm really sorry. I sort of sat down with the team and tried to figure out what the issue was. It's a technical bug with the project data and the project itself. We will fix it and we'll let you know. Really sorry about the delay. But okay. Anyway, thank you. Let's sort of get started with the topic for today, right? Today we're going to learn a very interesting idea. As for the age of this idea, right? Just like convolutional neural networks had pretty much been invented by 1997. In the same way, recurrent neural networks had been invented in 1986 or 87. Like, it is that old. This idea of recurrent neural networks is kind of old, but people only just got it to work recently. Okay. The main difference, why were people not able to do it well in 90s versus why we're able to do it now, is 2 reasons. First one is computation, right? We did not know how to use GPUs to accelerate stuff back then. And second reason is because they have a much better understanding of what works and what doesn't work in terms of activation functions. So the activation functions kind of play a big role when it comes to recurrent neural networks. Let us see, right? Let's see this today. Okay, so let's get started. As usual, I'm going to start with a quick recap of all the major concepts we've discussed so far, and hopefully that will help us understand what is the delta, right? What is new about RNNs and how are they able to address problems with all the approaches we've seen so far. So let me just run through this really quick. We began with the problem of converting text data to vector form, right? We studied different strategies. One strategy was doing document vectorization, where if you have a corpus, you're interested in getting one vector per document rather than one vector per word. Okay, document vectorization is the first part. The strategies we studied there was bag of words and TF-IDF. Then we went to word vectorization, where every word gets a representation. And then there is some semantic meaning captured in that vector space. Okay, so word vectorization, we saw continuous bag of words and skipgram. Then we went on to language modeling, where our task was basically to predict the next word. Right? If you train a computer to try and predict the next word, inherently it has to learn a very good representation for the meaning behind the words. And that is why we called this task as language modeling, because now the computer is learning how to capture meaning from the text, right? And finally, topic modeling is what we studied last class. Heuristics and latent dirichlet allocation were the methods we discussed. Broadly speaking, topic modeling was extracting, abstract ideas out of our text, right? Okay, so Arun says LDA a little bit more, like Gibbs distribution. If you can throw some light on LDA. Sure, Arun. I'm not entirely aware. So I guess the Gibbs distribution, let me just look that up. Let me refresh my memory. Yeah, I believe a Gibbs distribution is to the that distribution, right? Okay, it's kind of related to. Okay. Oh, I see. Definitely. So let's do one thing, Arun. Let's sort of take it up at the end of the class. How about this? I will help you figure that out, right? I don't have the answer ready right now, but I will help you figure this out. Kindly raise a question on the questions tab. Thank you. Okay, cool. So let's proceed, guys. So this is a broad overview of all that we have studied. Okay. So the agenda for today is to first introduce recurrent neural networks as a network architecture. Okay. We are going to see what is the fundamental change we have to do to our architecture or our understanding of neural network architectures to get this stuff to work. Then we are going to see different variants of this and its applicability in different types of tasks. Then we are going to come to training and backpropagation through time. So there is a concept called propagation through time, which is required for training this recurrent neural network. And that is what we're going to study. And finally, we're going to apply this to solve a business case, right? So first, let's begin as usual by discussing what the business case is. Okay. So the business case that we are going to study today is how to classify a headline into a relevant category, right? Fundamentally speaking, news headlines are basically like a one-liner which captures the essence of the entire article, right? So technically, if we know the headline of an article, we should be able to tell which field it falls under, right? So let's take an example of this. So these are the usual inputs. This is a cell which allows you to download the data set. Let's kind of see the data set that we have, okay? So what I want you guys to notice here is we have a label column over here, which is known as category. So if you notice, this category is defining the broad area the news article is following, right? For example, you have ad sales, boost, Time Warner, profit, and Greenspan speech is also business related. Then you have tech related articles like BT program to beat dialer scams, spam emails, tempt net shoppers, stuff like this. So our main task today is to take the title of this article and predict what the broad category is. Okay. Of course, we have studied a lot of techniques already, which could allow us to do something like this, but we're going to change our approach today. We're going to analyze very critically what was missing over there and what can be done to solve those problems. All right. Okay. So let us quickly understand the data set a little bit better. Let's try and understand what are the different categories and what is the distribution of a class. Because at the beginning of any machine learning problem, you have to see, do I have a class imbalance problem or not, right? Okay. So it turns out that the distribution of categories in this data set is as follows. You have 500 odd articles in sports and business. Then you have 400 odd articles in politics and somewhere between 300 and 400 articles for tech and entertainment, right? So broadly speaking, we can say that our data set is kind of well distributed. Okay. So now that we have understood this, right? Now that we have understood the broad distribution of our data set, we can proceed for solving using the approaches we've already learned. Okay. Based on techniques that we have already seen, anyone wants to propose an approach, sort of discuss and see what we can. Okay. Oh, I see. Voice is breaking. Just one moment. Let me just check. Oh, okay. Voice is breaking a lot. I see. Just give me one moment, guys. Guys, am I audible now? Is this better? I kind of disconnected and reconnected to a better hotspot. Am I audible now? Okay. Cool. Let's see if this works. Worst case scenario, what I might have to do is I might have to turn off my video for a while. If the lag continues, right? I might turn off my video for a while. Okay. Cool. So just want to understand at what point did my voice start breaking? Did you guys understand the data distribution and the problem? Can I just have a quick confirmation? Oh, okay. Minor lags are still there. I see. Cool. Let's do one thing. I'm going to turn off my video for a while, and yeah, it's probably going to get better if I disable the video. All right. Is my voice kind of better now, guys? Is this better? Okay, perfect. Are there still any lags? Okay, cool. All right, guys. So let's. Okay, no lag. Right? Perfect. Okay, thank you. Cool. Just a quick question. Problem statement clear to everyone today? Yeah. So the basic problem statement that we are solving today is, oh, okay, still there. I see. Okay, cool. It's still lagging, huh? Just one moment, guys. Let me fix this. Oh, I see. I see, Deepit. I'm really sorry about that. Guys, does this fix the problem? Does this fix the problem? Uh, is my voice audible now, or is it still lagging? Hey, guys, am I still audible? Can I get a confirmation if I'm audible? Okay. Seems to work now, but minor lags. Okay, mostly working. Let's do one thing. I'm going to try and change the resolution of the screen share. Okay, okay. It's kind of better now, right? All right. So let's sort of do this. One moment. Guys, just give me 1 second. I'm screen blurring is there, right? Yeah. Let me just check one thing. Okay, is this better? Is my screen readable now? Okay, perfect. And if there is any lags, right, guys, please let me know. All right. I think it should work now. I switched to a better network, but yeah, hopefully this should work now. All right. So let's resume our discussion with the problem statement that we're trying to solve. All right. The problem statement that we're trying to solve today is uh, categorizing the news articles that we have at BBC. Right. We're imagining that we are data scientists at BBC. We have to build a network which can take the title of a news article and predict what category it belongs to. All right. Is the problem statement clear to everyone, guys? Okay, cool. So this is what we have to solve today. All right. Uh, our data set looks like this. Broadly, there are 5 categories over here. We have sports, business, politics, tech, and entertainment. And what type of classification problem is this? Can you guys quickly let me know? Is it a binary classification problem or it's a multi-class classification problem? Okay, cool. So have we studied approaches? So in everything that we have done so far, right? In everything that we have done so far, have we studied enough techniques to approach a multi-class classification problem? Yes or no? Yes or no? Yes, we have, right? Okay, cool. So now with your help, I want to try and understand if I gave you this problem without the requirement that you have to build an RNN, I want to understand how you guys would approach this. All right. So broadly, we have sequences of text which looks like this. So let me read this out. Right. Let us say that this is the first 3 sentences of an article that I have written. The sentences are: I traveled to France last December. A CV conference was held at Nice. It lasted for 3 days. So among the categories that we have defined over here, where would you put this? Which category would this fall under? Tech, right? Because it's talking about a CV conference. So it has to be a tech related article. Okay, cool. So happy to know that you guys are able to understand the problem. Okay, so if I now ask you to sort of take these sentences and build a multi-class classifier which puts it into the appropriate category, what approach would you use? Can anybody help me with an approach? What is the first thing that comes to your mind? I want to understand that. Anyone? OVR? Okay, perfect. So, so what is OVR? I believe you mean one hot encoding vector? No. What do you mean by OVR? Oh, one versus rest. Okay. Multi-class classification problem, one versus rest. Agreed. Fine. But one versus rest classification is what we apply when we have a good binary classifier and we can apply that to multiple cases, right? What I'm trying to understand is how do we deal with this text data here? Okay, perfect. Now I'm getting some good responses. Amit says cascade OVRs. I totally agree with that. Can I try and do this directly with a neural network architecture? So yeah, cool. Amit, softmax also works in this case. Perfect. I like Indradeep's suggestion. First, I will convert the doc to TF-IDF. So approach one is doc to TF-IDF, right? Once I do this, I can basically feed it to any general binary or multi-class classifier, right? Multi-class classification problem. So what are the different multi-class classification problems you guys have come across? I can apply something like I don't know. I can apply SVMs or something like that, right? SVMs or you know, uh, yeah, decision trees. And what else can I apply? Okay. Right. So essentially this approach. So let's talk about abstract in an abstract sense. What is it that we're doing here, right? At an abstract level, first of all, we have text data over here, and we have already learned that to deal with text data, we have to first vectorize it. Okay. I really appreciate that you guys figured out. I have documents over here, right? So if I have documents over here, a TF-IDF kind of vectorization strategy is what we should go for, because I want to classify at a document level, not at a word level. So I really appreciate the thought that, okay, we can take all the documents, we can convert them to TF-IDF vectors, and then we can use some general multi-class classification problem to solve this problem. Okay, cool. So naive Bayes is one method for this, linear SVD is another method, fast KNN is another method, decision trees, all these methods are valid. Perfect. Okay. Anyone wants to try and approach this problem from a neural network perspective? From a neural network perspective, do you guys want to approach this problem? If we wanted to do this using neural networks, what neural network approach have we learned so far, guys? What approach have we learned so far? Neural networks. We use neural networks for something so far, right? What was it? Can somebody tell me the name? Can I say I can do word to vec? Is it okay if I do word to vec? Okay, word to vec is another approach, right? Okay. So let's now look at neural network approaches. So, okay. So now let us try and imagine a neural network approach to this. A neural network approach to this could be something like, okay, I have this textual data with me, right? Can you guys tell me, is the lengths of these sentences the same? Let us try and understand what are the lengths of each sentence, right? Let us say this is word number 1, this is word number 2, this is 3, 4, 5, 6. The next sentence, it is 1, 2, 3, 4, 5, 6, 7. The next sentence is 1, 2, 3, 4, 5, right? Okay. So, cool. So if I have now variable length sentences here, right? Variable length sentences, or if I have variable length inputs to my neural network, how do I generally handle that? Is it possible for me to do that? First of all, is it possible for me to handle these variable lengths? No, right? Of course not. Guys, I think my network condition has improved, so I'm going to try keeping my video on for a while. If it goes bad again, I'm going to remove. Okay, so Arun's idea is clip. Perfect. I really like that idea. Okay. Let's do that, right? Okay. So neural network approaches. Our first problem 1, is length of inputs is varying. Agreed? The solution that Arun has given me is very nice. Let's discuss this solution. The input. Okay. So let me explain the solution to you guys first, right? Yes, Indradeep, you're absolutely right. So I want to now explore the suggestion that Arun has given here. Okay, cool. So let me explore the solution Arun has given. So Arun's solution works a little bit like this, guys. Essentially, what I want to work with today is all these titles, right? So if I take these titles over here and I basically try and record the length of each title. Okay, let us say the first title's length is say 7, the next title's length is say 20, the next title's length is say 5, something like that, right? Okay, actually I can count it here. 1, 2, 3, 4, 5, 6, 7 is actually right. 1, 2, 3, 4, 5 is the length over here. And let us say the length over here is say what, 1, 2, 3, 4, 5, 6, right? And so on. I basically go and I see all the lengths in my title. And basically, if I find the max length of this, right, I can simply take the lengths of all the titles. I can calculate the maximum length. Let us assume, because it's a newspaper article, right? Of course, there are going to be some constraints. Nobody is going to allow you to put a 30 word newspaper title, right, for an article. Let us say the max length is say 12 words. Okay. I really like Arun's suggestion. Arun says, let us take these words together. Let us create a neural network where I have only 12 inputs. Okay. So essentially, I have 12 inputs to my neural network. Okay. And if in case the length is lesser, what I can do is I can simply pad it, right? I can take this ad sales boost times Warner profit, and I can define a new word, which is something like blank. Okay. I can introduce this new token in my data set, and I will basically pad this with how many do I need here to make it 12? I'll need 5, right? I'll need 5 blanks over here to make it 12. So now what I'm going to do is I'm going to take this title, I'm going to pad it with these 5 blank words, and then I'm going to feed it to my neural network architecture. Okay. Does this seem like a good solution to everyone? Have I now dealt with the problem that neural network which requires a fixed dimension, right? Neural network which requires a fixed dimensional input, I'm overcoming that by making sure all the inputs are 12 words, correct? Does this solve the problem, guys? Is this okay, first of all, with everyone? This is okay, right? This is good. All right, cool. So this is one way to do things. Perfect. Okay, what is the next problem with this neural network architecture? Something we've been discussing for many classes. Indradeep's question is, but input will be sparse, right? So Indradeep, what I'm going to do is I'm going to assign each word with an index. Okay, I'm going to code it. So my vocabulary size will be 50,000 or 5,000 or something, right? What I will feed to my neural network is actually just the index, right? So I can still create a neural network architecture which takes the index of the words, not the whole one hot encoded vector. I'm only going to give the index of the words to my neural network architecture, and I'm going to ask it to do something, right? Does that seem like a valid strategy? Does that solve the problem? Okay, perfect. Cool. So this is a problem with it. This is the ad hoc solution that we have arrived at. And trust me, guys, somebody somewhere on earth has tried this approach. Okay, somebody somewhere on earth has tried this approach. It did not work so well, which is why we have to go for better stuff, right? So let us now try and understand what is not okay with this right now. Okay, and I've been hinting at this for a very long time, right? One thing that we have really not solved for so far with all the methods that we have. Okay, that's the hint for you. What is one critical problem with this architecture? Context. Exactly, right? Context, long range context. There is no way. See, the idea is this, okay? I can jumble up the words in my title and I can feed it to my neural network. It will still give one output, right? It will still give one output. That is wrong. We now have to think of a way for this neural network to remember what was the context 5 or 6 words back, right? To some extent, we had solved this problem. Can you guys tell me quickly? Last 2 classes we've been discussing one way, right? We solved this problem to some extent. What did we use? What was the concept that we used to solve this problem? No. LDA heuristic stats is okay. N-gram. Yes, Amit. Perfect. N-gram is what we use to capture contextual information, right? We said that don't just look at the current word I'm giving you. Look at 3 or 4 words behind. We had the freedom to choose the thing, right? We had the freedom to choose the number of words I can keep for context. So now let us use this idea to build a neural network architecture, okay? So problem 2, is context information. Okay. Problem 2 is context information. The solution is exactly what Amit just told us. N-grams. Okay. Force the neural network to see n words at a time. Okay. Now I want you guys again to put your critical hats on. Okay. Whenever we are criticizing a method, we have to point out to a serious problem with this method. Can you guys point out to a serious method with this problem? A serious problem with this method? Anyone? Anyone wants to take a guess? Okay. First problem was length of inputs varying. I fixed that problem. Second problem is context information. Let's fix this problem. What is one serious problem still with n-grams? Length of the gram, right? Length is very, very difficult to handle. Length of the n-gram is very difficult to optimize. Can you guys tell me, as I increase the length of my n-gram, right? As I increase the length of my n-gram, isn't it that I will have exponential increase in the length of the input vectors? Once I start taking different combinations, right? The size of my network is now going to shoot up, right? The major problem. So if I were in your shoes, I would have confidently said that the major problem with this is time complexity and space complexity. This is the major problem number 3. Okay. So we had length of inputs varying. We solved that problem. We had context information missing. We solved that problem with n-grams. Now the issue is time and space complexity. It is very, very expensive to train these networks. So now what's the solution, right? So what's the solution to these 3 problems? Okay. The solution turns out is an architecture which looks like this. Okay. I'm going to just show you the architecture and I'm going to pause there for a while. I want you guys to see this and I want you to complain to me that actually we have not understood anything. This is not making sense. So yeah. So for the first time, I think I'm showing you a neural network architecture where it is feeding onto itself, right? What is this called as in a graph? What is this called as? Anyone? This kind of an arrow where I take one input and I feed it back to itself. It's a loop. It's a cycle. Exactly. Cycle, loop back. All of these are correct terms, guys. Feedback loop. Exactly. Perfect. I was looking for feedback loop because that is what a signal processing guy would have told me. Okay. This is a feedback loop. Yes. Anindya, yes. Backward propagation is going to be a problem here, but we will see what that problem is in a short while. Okay. Cool. So this is the architecture, which is the solution to all of these 3 problems, guys. Length of the input is varying, contextual information is missing, time and space complexity is lost. All of these are problems here. Okay. All of these are problems which are solved by this architecture. Before I go into the depth of this architecture, right, I want to give you guys a small analogy over here to understand this really well. Okay. If you think about it, the problem with this n-gram approach, right, was that my network was not able to remember contextual information, right? It was not able to memorize contextual information. If you really want to memorize contextual information, you have to give the neural network something which is known as memory. Okay. So the main motivation behind this RNN architecture, okay, is the following. Neural networks lack memory. How do we give it memory? Right? How do we give it memory? The answer is we will explicitly define one vector which is called h of t. Okay. In RNN literature, this is known as the hidden state. Okay. In RNN literature, this is known as hidden state. What we have to do is basically we have to now figure out how this hidden state is achieving the purpose of giving this neural network memory. Okay. So in any task in general, if it looks like your neural network has to memorize something, the solution in general is always introducing a cycle. The cycle, the advantage of a cycle is like you're allowing your neural network to revise concepts it has already seen before, right? Does this make sense to everyone? Does this make sense to everyone? The major missing thing in our architecture was memory. We are giving it memory by introducing a hidden state. Does this make sense to everyone? I'm going to pause here. Okay, so we are now going to introduce this memory component. Let us now dive deep into this architecture and see how this memory is coming. Okay, so the major concept here is if I want memory anywhere in my architecture, I have to introduce a cycle. Okay, that is the main takeaway I want you guys to have. Okay, now let us go and see how to actually get this done. Right? Okay, so this discussion is simply what all is missing in an NLP. Right? How do we capture contextual information? Right? This is solved by this architecture, which is an RNN. And the main idea over here is we are giving our neural network some memory. Okay. So RNN is a special type of neural networks. Okay. Let us now try and understand how this RNN is being unraveled over time. How is this architecture actually helping? Right? Let's sort of take this up. So I'm going to copy this over there and let us now try and understand what's happening over here. Okay. Cool. Okay. So first of all, if you guys notice now, the input to my RNN is this X of T, right? My question to you is, what is this T, right? What is this T? How is it helping over here? That is the first question, right? Okay. So now I'm going to introduce a certain type of data that we have been talking about, but we have never really quantized. Okay. The type of data that we're going to start talking about now is sequence data. Okay. Sequence data. You guys have come across sequence data in the ML2 module. Do you guys remember where you have come across sequence data? Where have we come across sequence data? Time series, right? Perfect. So what is the major change between time series data and normal data? Every observation, okay, every observation. So what are our observations here? Our observations are these individual words. Okay, these are our observations. Now, I don't only have to care about the word, I have to also care about its position in the whole sentence, right? So now what I'm going to do is from now onwards, okay, we are going to start looking at all the text data that we have as a time series, okay? From now on, I don't only care about the word, okay? I'm no longer one hot encoding. Along with the word, I'm encoding this positional information as well. And this is the major change in the data set which is required for RNNs to work. Okay, cool. So is everybody clear now how I'm going to encode things? If this is my sentence, I'm going to say I is the first word. So T. So now this variable which is capturing this index, right? I'm going to call that variable as T. Okay. So when I feed the word I have to say T is equal to 1. When I feed the word traveled, I have to say T is equal to 2. When I say the word France, I have to say T is equal to 4. Okay. And if I am giving this entire thing as input, I have to make sure that my time is properly encoded. I am not allowed to arbitrarily restart the time. Okay. The time now has to be what here? So if this is 1, 2, 3, 4, 5, 6, which is this word in this data set? What is the index of this? No, it's not 1, right? I cannot arbitrarily do it. This is a sentence now. So now the encoding should be 7 over here, right? Because I have to correct this. So 7, 8, 9, 10, 11, 12, 13. Okay. And then when I'm feeding this part of it to my network, I have to say 15, 16, 17, 18, 19. Okay. So this is the major change, guys. From now on, I'm no longer just thinking about these as words. I'm thinking about these words along with this index over here. Okay. I hope this is clear now. Cool. So now let's take this small example. Let me take this example and let us take it there and try and understand how we will feed this data to our RNN. Okay. So I traveled to France last December is my first 6 words. Let me take this over there and let us try and understand how we will give this to our RNN. Okay. So the sentence that I have is I traveled to France last December. Oh, sorry. Okay. What are the indices here? 1, 2, 3, 4, 5, 6. Okay. These are my indices. So guys, how am I now feeding this into my RNN? Let us understand this at a very high level, and then we will go and see inside what this RNN, what's happening. Okay. We're going to break this problem down. First, let's understand how this is being fed. Okay. So the first time what I'm going to do is I'm going to give it the word I. Okay. To this RNN. So I'm going to, so let us imagine now I have this as x of 1. Okay. X of 1 now is going to be this word I. How do I give this word I to it? How do I give this word I to it? Can I use one hot encoding to give the input? Can I use one hot encoded version of this? Do you guys think that's okay? No? Why not? Why not? Why not? Okay, what's the problem with one hot encoding? What's the problem? Loses context there? Okay. So Arun, no position information? Okay. One hot encoding doesn't have index of the word. All right. So let me argue now why one hot encoding is okay over here. Okay, guys. So broadly speaking, guys, what I'm saying is I'm going to capture, okay? I'm going to capture the index in a slightly different way. I totally agree that by on its own, right? On its own, one hot encoding will not do this properly. But now what I'm going to do is I'm going to now define that. I'm going to define the size of each of these vectors. Okay. I'm going to define the size of each of these vectors. And this is how I will do it. So first of all, guys, let us try and analyze this term, right? Recurrent neural networks. Neural networks, everyone understands. What does this word recurrent remind you of? Any concept from our computer programming, from our Python days? Anyone? Recursion, right? Recurrent should remind you of the word recursion. Okay? It should remind you of the word recursion. What is the meaning of the word recursion? The meaning of the word recursion is I'm going to keep calling the same function on my input over and over again. Okay? I'm going to call the same function on my input over and over again. Okay? So this is how we disconnect the word from the position in an RNN. Okay? I'm first going to give a one hot encoded vector of this. So let us say that for my corpus, the vocabulary size is 5000. Okay. Let us say that xt minus 1, xt plus 1, xt plus n, all of these are 5000 length vectors. Okay. Let us say that these are 5000 length vectors. Okay. How am I encoding time over here? Right? Let us see that. So what I'm going to do is I'm going to take this word, I'm going to convert it to its one hot encoded label. Okay. One hot encoded, not label, one hot encoded vector form. And I'm going to give it here. Okay. Then this RNN is going to do something, some computation internally. It is going to give me this OT minus 1. Okay. This is the output at T minus 1. And it is also going to give me this other output, which is known as the hidden state. Okay. This other output that I'm giving it is the hidden state. Okay. Cool. So when I give one hot encoded vector to my RNN, it is going to give me two outputs. The two outputs are this output here, OT minus 1, as well as this hidden state over here. Now what I'm going to do is, for the next iteration, I'm going to pass this h of t minus 1 to this RNN, and I'm going to feed the next word with one hot encoding. Okay, next word over here. What is different between the first input and the second input, guys? The main difference here is this hidden state. Okay, the hidden state is something which is allowing the RNN from this iteration to tell the next one what it has learned about this word. Okay, so this hidden state is now going to take care of this encoding of the position. Okay, the encoding of the position of these words is going to be taken care of by the hidden state and not by this x t minus 1, x t minus 2, all this. Okay, this is how I'm dealing with sequence data through this cycle. Okay, cool. So let's continue. Now, after I have introduced this word traveled with one hot encoding to this RNN, it is also getting this h of t minus 1 from the previous state. It is going to use both of these inputs to calculate the next output as well as the next hidden state. Okay. Then when I feed this vector, when I feed this word into it, OHE, I will apply one hot encoding here. I will put it over here. This RNN is now getting the contextual information of the previous two words through this hidden state. Okay. This hidden state will now take care of capturing all the context information I need from here. And now when it sees the word two, it not only has the one hot encoded version of the word here, it also has contextual information from the previous two states. Okay. This is what I mean by memory, guys. This is exactly what I mean by memory. Over here, the memory is being captured by this hidden state. So this hidden state's job is to memorize something about this word when it saw it. It's memorize something about this word when it saw it, memorize something about this word. And finally, when I give the word December to it, right, with one hot encoded, when I finally give this word December to it, it will be the job of the hidden state which is coming here to encode all the contextual information from before. And finally, this RNN will give me this output. Okay. Is this idea clear to everyone? How I'm going to now use sequential data along with hidden state memory to carry forward my computation. Okay. This is the major change, guys. This is the major change. Okay. I'm going to pause here in case anyone has any doubts. Guys, this is a very fundamental concept. If there is any doubts here, please ask me now. Please ask me now. Sincere request. Have you understood how we are feeding the sequence into my RNN? Okay, cool. One person has understood in a class of 26. I hope the others have also understood, guys. If you have doubts, guys, please ask. Okay, all right. Okay, so we have now understood how this RNN is capturing the sequence information. The sequence information is being captured by this hidden state, the memory component. Okay, this is the memory we have introduced here. So how we're interpreting the cycle is we will keep on feeding inputs to this. Okay, we will keep on feeding inputs to this, and as and when the inputs keep getting fed into this, it will keep giving us an output, and it will encode a hidden state, and it will keep feeding that hidden state to itself. Right? It will keep feeding the hidden state to itself, and that is how it will memorize sequence information. I have a very nice question in private chat from Anindya. Doesn't this lead to overfitting? Is it not possible that my hidden state will be overfit? No, Anindya. This hidden state is not something which we fix. This hidden state is something which gets generated every time you pass a word here. See, that is the beauty of an RNN. Okay. The output it gives h of t. So now the output of the RNN is not only depending on the input you're giving it. It is also depending on this hidden state. This new hidden state will get generated every time it sees a new sentence. So it is like we're telling our neural network, I will keep giving you sentences. It's your job to remember important stuff from the sentence and then give me some output. Okay. So this is how it is not going to lead to overfitting. Beautiful question. All right. Any other doubts, guys, at this point? Okay. I am going to assume no more doubts. So let's do one thing. Okay. Let us take this architecture, and I want your help to understand how many hidden states are going to be there for the sentence I give you. Okay. Let's do this. I want your help to count how many hidden states are required. Okay. Cool. So let me take this architecture. Let me paste it here. Okay, it's not getting pasted. One moment. I'll just do that again. Yeah. Okay. Cool. Now, Garfield is a cat. He is fat. Okay. I have these two sentences. In this, I have 1, 2, 3, 4. And I want you to think of these two sentences as different inputs for this. 1, 2, 3. Okay. Different inputs. Okay. So I want to now discuss with you how to count how many hidden states will be required to encode this sentence. Okay, cool. Satish's question to me is how many words does a hidden state hold? Satish, even if I give 100 length sentence to my RNN, it'll hold the hidden state's responsibility is to encode all 100 for that input. Then if I give an input for 3, then the hidden state will have to encode all 3. So there is some issue with this. Of course, this is not the final thing that is going to give you ChatGPT. We will have to solve some problems with RNN also. This is a good question which tells me what possible problem could be there, right? The problem here is for this 4-length sentence also the same hidden state has to encode all 3 words before. And for the 3-length sentence also the same hidden state has to encode the 2 words it has seen before. So the hidden state has to hold as many as it can. Okay, it has to hold as many as it can. That's the answer. Cool. Yes, Amit has made this observation in private chat to me. As the length of the architecture increases, hidden states lose the context from very starting of the sentences. Perfect, Amit. So this is one problem of the RNN that we're going to solve next class when we see LSTMs. But for now, let us go ahead. Okay, cool. So how many hidden states are required for the first sentence, guys? So I will have one hidden state output for this one. I will have one hidden state output for this one. I will have one hidden state output for this one. And I will have one hidden state output for this one, right? So the total that I have are actually 4. Okay, over here, as I give this input to my RNN, it will create 4 different hidden state vectors. And if I now give this sentence to it, can you guys quickly count and tell me how many it will give me? How many hidden states? For this one, the second sentence, just imagine I'm giving this second sentence only to my neural network. How many hidden states will be created? 3, right? After this input goes, it will create one hidden state. After this input goes, it will create one more hidden state. After this input goes, it will create one more hidden state. So 3. So in general, whenever we have an RNN and we're giving it a sentence, which is say 4 words long, it will create 4 hidden states. If we give it a sentence which is 100 words long, it will create 100 hidden states. Okay, it will create this and it will keep passing it forward to itself, right? That is how it's working. Okay, now guys, there are some variants to this. So let us quickly discuss what are the different variants of this RNNs. Okay, so this is a very nice image which has been taken from this Andre Karpathy's blog, where he talks about the beauty of the unreasonable effectiveness of RNNs. Okay, he talks about the unreasonable effectiveness of RNNs. You guys can check out that blog. The link is there in this notebook. Please check that out. It's very interesting. But for now, let us try and understand what are the different types of RNNs. Okay, so if I have a one-to-one RNN, right? If I have a one-to-one RNN, this is our normal feed-forward neural network because there is no real hidden state coming back to this, right? In this kind of a thing. So this is a normal neural network architecture, no hidden states generated here. Then we have a one-to-many. So for a single input, I have to generate many outputs. Can somebody remind me what kind of task have we seen which follows this category, which falls into this category? What task? Essay writing? Exactly, right? Exactly, Indradeep. Essay writing. Skip grams, exactly, right? Skip gram is also something like this. We give one word and we expect multiple outputs and we want these outputs to somehow be connected with each other, right? So if we just take a skip gram, because there's no context information there, the skip gram may return random words to you. But with an RNN, because this hidden state information is moving to the next word, right? When it is generating this word, it will have hidden state information about this word that it has generated. Okay, that is why it will be able to generate this word which is connected to this word. And essay writing is one to many kind of thing. We will give one topic, we will ask this network to give us one full sentence about this topic, something like that. Then we have this many to one. What is many to one? CBOW? Okay, CBOW, perfect. CBOW is many to one. But what is the task? TLDR, perfect, right? TLDR. In fact, guys, isn't the problem we're trying to solve today also many to one? Topic classification. Yeah. So this topic classification is also many to one problem. Okay. So this is the architecture that we'll be studying in detail today. This type of RNNs is what we'll be discussing today. I just want you guys to be aware of all the other types as well, so that if you encounter it, you will know that whatever we study today can be applied to understand these things. Okay. So that is what. Cool. Now let's try and understand these other types of architectures. We have many to many, but we have two different types of architectures. What do you guys notice here? What's the main difference between these two? What's the main difference between these two many to many architectures? Is it okay? Output starts after all inputs. That is one thing, right? This is a delayed kind of RNN. This is a delayed kind of RNN. If I'm giving my inputs, I don't want it to give me output till I have seen the whole input. Versus many to many, where I'm giving the sentence for each word that I'm giving it, I want an output, right? Okay. So guys, we have actually done one thing last class which requires this kind of architecture. Do you guys remember the heuristic approach that we did? We required one thing, right? From Spacey. What was Spacey doing for us? What was Spacey doing for us? Parts of speech tagging, right? Exactly. So if I want to solve the parts of speech tagging problem with RNNs, then I can use this approach, right? I can use this approach if I want to do many to many. For every word that I'm getting, I want a part of speech output. So for parts of speech tagging, you can use this kind of many to many architecture. For this, can you guys tell me what kind of task will fit here? Can you guys guess? When will I use this? When will I use this? Summarization? Encoder, decoder, perfect. Summarization is a good task. Dialogue monologue is a good task. So basically it's like question answering, right? Question answering. So if I give this as a question, I want the answer to start only after it has seen my whole question, right? So you can think of this as a question answering sort of system. So when we actually discuss something like large language models, we will be seeing these kinds of architectures coming into play. Okay. So when we start discussing things like how does BERT work or those LSTMs work, LSTMs will follow something like this to solve those kinds of problems. Cool. Okay. So when it comes to RNNs, these are the different types of architectures we can use. Cool. Any confusion at this point? Any confusions, guys? Okay, I'm going to assume there are no confusions and I'm going to move on. Okay, now let us dive a little bit deep into how this architecture looks like. Okay, let us now dive deep into how this architecture looks like. For simplicity, let me just zoom out a bit. I'm going to copy this over there and I'm going to show you how this architecture works exactly. Okay, cool. So now let us dive deep into the architecture of this RNN. So let me title this RNN architecture deep dive. Okay, cool. So first let us try and understand what this XT is, right? What is this XT, guys? What did we decide for our XT over here? The input to our RNN. What is this XT? This is the input, right? This is the input. So this is one possibility is it's a one hot encoded OHE word. Okay. Instead of one hot encoded word, can we use something better? We basically just want a vector representation of a word, right? Yes, we just want a vector representation. Can we do something better than one hot encoding? Can we do something better than one hot encoding? Word to vec, right? Perfect, guys. Perfect. Word to vec is another option. Okay. So it is like we can pre-train a word to vec model. We can use that word to vec model to give us one vector per word, and then that can be the input to this. Okay. There is actually a third alternative here, a real-time word-to-vec. So sorry, no, 1 minute. Let me separate these two out slightly better. I think it makes more sense if I say this is fixed word-to-vec. So one version is fixed word-to-vec and trained word-to-vec. Okay. Do you guys remember in transfer learning, when we took a network and we plugged it in, right? We had an option to train that network or keep it as it is. You guys remember this from our computer vision days? You guys remember? Just hit a yes if you do, guys. Important. Okay, cool. Yeah. So we had an option of freezing, right? So the second option that I'm talking about here is where we freeze the word-to-vec. The third option is where we allow the word-to-vec architecture to be trained as we are feeding our input. Okay. And generally, which one do you think will work better based on what we have seen in CV? Which one works better, guys? Does training work better? Trained works better, right? So in general, people prefer this method. This is the most preferable out of all of these three. Okay. So whenever we're supplying inputs to our RNN, we have three options. We can give the one hot encoded vector as it is. That is not a great way to do it. We can use fixed word-to-vec, where we pre-train a word-to-vec architecture and then feed it in. Third option is to unfreeze that and allow it to be trained as the network progresses. Perfect. So these are the three options we have for this XT. So I hope it's very clear now. This XT is basically a vector representation of our word, input word. Is it just any word or is it word at time t? Is it just any word or is it word at time t? What do you guys think? It's word at time t, right? It's word at time t. At time t. This is important, okay? That is a fundamental change. Whatever we're giving as input to our RNN, it has to be at time t, okay? Cool. Now, once this vector comes into this architecture, what we are going to have is we're going to have this matrix called W. Just 1 minute. I'll just want to be consistent with the notation that we're going to introduce later. Let me just check that. The notation that I'm going to introduce later is hx. Okay. So we are now going to take this vector and we're going to multiply by this matrix called WHX. Okay. Cool. This is, what kind of layer is this? What layer does this? It takes a vector, changes the dimensions. What layer is this in Keras? How would I implement it in Keras? Keras dot layers dot what? Keras dot layers dot what? Come on, guys. This should be easy. We've been studying Keras for a long time. Oh, repeat? Dense. I'll repeat the question, guys. I want to take this vector x of t that I'm feeding into my layer. I want to change the dimension before I feed it forward, right? This vector representation will be something like 100 or 1000 dimensions. But now for my hidden state, I want to keep the dimensions to something like 200 or 300, something like that. So I basically want a dimension change before I allow this to go forward. So the kind of layer that I will use to do this is nothing but the dense layer. Yes, Arun. Deepit and Arun, you're absolutely correct. Amit, are you convinced? The layer that I will apply after this comes in is a dense layer. Okay, it's a dense layer. The dimensions of this matrix will decide what is the output size. Okay, so this I'm going to multiply with the dense layer. Okay, now for t equal to 0, right? T equal to 0, I have multiple options for this hidden state. Okay, for this hidden state, I have multiple options. At t equal to 0, I can say h of 0 equal to 0 vector. Okay, I can say that this h of 0 is a 0 vector, or I can initialize randomly. Okay, randomly initialize it for the starting point. Or the third option that I have is h of 0 is some fixed vector. Okay, all three options have been tried in the literature, and what people have found that fixing h0 to some fixed random vector is the best way to do it. Okay, This is the best way to do it, because we want to basically ensure that the hidden state for zero state is well defined, right? It's well defined. Why having zero is not a good idea? Do you guys remember from neural networks classes? Why should we not keep anything zero? It'll be problematic somewhere. Where do we get problems if we keep zero inputs? Backpropagation. Do we have problems in the way backpropagation happens? Symmetric, yeah, convergence in backprop is a problem, right? So out of these three strategies, the best strategy is this one. We have to take the H0, we have to fix it. Slow learning in the beginning. Perfect. All of these are valid answers, guys. So because I have to now make sure that my vector is encoding the zero state, right? Where I've not seen any word. The best strategy for this H of 0 is to initialize it to some fixed vector and keep that vector in mind. Okay, at t equal to 0. Fine. So now once at t equal to 0, this vector is some fixed vector. What we're going to do now is we're again going to apply a dense layer over here. Okay, and let me quickly check the notation again. This is WHH. Okay, guys, this is WHH. So once this hidden state is coming input, I'm going to multiply this hidden state by this WHH, and the output dimensions of this and the output dimensions of this have to match. Okay, they have to match. Why do they have to match? Because over here, I'm actually asking you to add these two up. Okay, I'm asking you to add these two up. So let us assume that we choose this size to be 200. Okay, let us assume that my input vector is 100 size. This hidden state is also the H0 is also 100. Just let me think for a second. I can keep the hidden state to 100. Yes. So let me assume that this input X is 100. This input hidden state is also 100. Now these two dense layers are basically increasing the length of these vectors to 200 before they're passing it. Okay. So now these two 200 length vectors are coming and they're getting added. Okay. Then this output of adding these two vectors is passed through a tanh activation. This is the activation that we generally use in a RNN. Okay. Can you guys quickly remind me what is the output range of tanh? What is the output range of tanh? -1 to 1, right? Okay. And what is the output range for the gradients? Do you guys remember this? How the tanh gradient looks like? Is it between 0 and 1? It's between 0 and 1, right? What problems have we seen with tanh activation so far? Have we seen some problem with vanishing gradients, right? Okay, let's keep this in mind, guys. I just want you guys to keep this in mind. We have a tanh layer sitting here, tanh activation sitting here. Whatever input vector I'm giving, whatever hidden state I'm giving, they're getting added up and we're passing it through a tanh. There could be problems with this tanh. Cool. Arun's question to me is there something like leaky tanh? No. So basically a tanh which has a small, okay, I see what you mean. Let me think about this. Is there something like that? Leaky tanh. I basically want to make sure it is increasing as a function of E, right? To the best of my knowledge, I have not come across any paper which uses leaky tanh, but I can think of how to define that function. We can discuss how to define that function if required, right? Okay. But for now, let us remember that this is coming to tanh. Okay. Once it comes out of tanh, right, guys, what is the output dimension going to be? So inside a 200 length vector is going to this tanh. What is the output dimension of tanh after applying tanh? Will tanh change? No, it won't, right? So 200 will be the output dimension. And now what I'm going to do is at this stage, I'm going to split this. Okay. Whatever output I'm getting after tanh, I'm going to next multiply this by a third matrix. I'm going to call this matrix WHY. Okay. WHY. I'm going to take this output vector, multiply it with this WHY, and I'm going to finally get my output at time t. Okay. Yeah. No, Sean. I don't think there's anything like leaky tanh, but we can figure out a system, right? We can define that function later on based on leaky relu. We can use our coordinate geometry knowledge to do that. Let's try it later. But for now, let us focus on how this RNN is working, okay? Now what's going to happen is this output which I'm getting after this tan h is going to be multiplied by this WHY, and we're going to get our final output. What should the output dimensions be, guys? What should this output dimension be? What should this be? 100? Yes, it has to be 100, Indradeep. It has to be 100. Why? Because we are encoding all our words into vector representations, right? And we want to make sure whatever output we're getting is a meaningful word. For that reason, we have to make sure that the output dimension over here is 100. Okay. So this WHY has to basically convert a 200 length vector to a 100 length vector. That's all we have to remember here. Okay. So this is basically reducing the dimension. Okay, cool. And finally, this hidden state is going to be nothing but this, whatever came out of tan h. Whatever came out of tan h, as it is, I'm going to pass as my next hidden state. Next hidden state. Okay. So this is how the architecture of an RNN works. Is this point clear to everyone? Is it clear to everyone how I'm going to convert my data to a sequence form, how I'm going to pass this sequence through my RNN, and how I'm going to get my outputs? If this is clear to everyone, we can take a break over here. Okay, cool. We can take a break over here. Before I do that, let me just address the questions. Yeah, guys, I'm really sorry I missed the questions. Let me address these. Indradeep's question is, after tan h, the dimension is 200 and ht minus 1 is 100 dimensional. Yes, you're right. Okay, so let me just make one small change. Let me say that for my entire neural network, right, this is going to be a 200 length vector. Let me define that. Oh, guys, am I not audible? Guys, is my voice breaking? No, right? Oh, okay, it's breaking for some people. It's good, right? Okay, Ajay, maybe I'm really sorry, but this time I think it's on your side. Ajay, can you just check your this one? Okay, some people are not able to hear me. Okay, let's do one thing. I'm going to just mute myself and unmute myself. Once I come back, I just want you to tell me again. Am I audible now? Is there still any breakage? Okay. So Ajay, I'm audible to everyone. Screen is visible to everyone. Is the screen? Screen is also visible to everyone. Guys, right now, if there's any breakage, guys, please check your internet connection. It's not on my side. Really sorry. Okay. So can somebody just message Ajay that screen is visible? One moment. I'm just messaging him. Yeah. Okay. Audible plus visible, Ajay. Just wanted to let him know. Now let me take this question. Okay, guys. Indradeep's question is, after tan h, the hidden states layer is 200, but over here I started with a 100 length vector. So let me just make one small modification. Let me say that throughout my network, I'm just going to use 200 length. Okay, that was a mistake that I made from my side when I started off. Sorry about that. Then the dimensions of this hidden, this will change, right? This will basically take 200 and it will give also 200. So this is going to be a square vector, square matrix. So the hidden state from now on is going to be 200 length. Just want to make sure that is clear to everyone. Okay. Indradeep, I hope that addresses your question. Now, Amit's question is input dimension equal to Amit. Yes, that was the answer to the question I gave that. Anil, dimension of OT and HT is same, right? No, Anil, the dimension of OT and XT has to be the same, right? Dimension of OT and X2 has to be the same, because XT and OT have to be words, but this hidden state does not have to be a word. Okay. Hidden state is like one extra variable that I have given to my network and say whatever useful you want, you store in this variable. Like that. Think of it that way. Is that clear? Is that clear? Anil? XT and OT should be the same, not hidden state. Hidden state is like, so I have the freedom to choose a much larger hidden state than the size of my words, right? that will make sure that it has enough memory to remember long range contextual information. So you can think of the dimension of this hidden state as the amount of memory you're giving your network to learn. Okay, think of it that way. It is a valid way to think of this. We will see this more in LSTMs, guys. We will see how LSTM's performance depends on size of the hidden states and all that. Okay, so now, guys, this is a logical point to take a break. Let us take a 5-minute break here, and once we come back, we will uh, discuss how front propagation, back propagation, and all those things work with respect to this. Okay. So Ajay's question is, what does the hidden state contain? Ajay, I'm giving the network full freedom to decide what the hidden state should contain. How am I giving it the freedom? I'm giving it the freedom by looking at this matrix over here, right? WHH. If you notice, hidden state is always going to be multiplied by this WHH, right? So this WHH matrix is what is in real time changing what this hidden state should contain. This WHS has the power to change this in real time. So if I give a long sentence, hidden states will be different. If I give a short sentence, hidden states will be different. Is that clear? Yeah. Yeah. Cool. So let's take a 5-minute. Oh, okay. There's one more question. One moment. So we have to learn three matrices via backprop. Yes, Indradeep. Totally, we have to learn three matrices via backprop. Exactly. Exactly. The three matrices that we have to learn are this WHH, this WHX, and this WHY. These are the three matrices that we have to finally learn. And this way, we can get our neural network to remember stuff now. Cool. So I'm going to start the countdown now. Let's meet in 5 minutes. And we're back. Can I get a quick confirmation that I'm audible and that you guys are back? Okay, perfect. Awesome. Few people are back. I think four people are back. So yeah, I think my network has improved, guys. So I'll see. Try keeping my video on for some time, and then we will go ahead. Right? Okay. So before I do that, guys, just one moment. I need to switch on my power plug. There is a low battery warning for me. I'll just do that. Sorry. Oops. Just give me 1 second. Yeah. Why isn't this charging? Okay. Just one moment, guys. All right. Is my screen readable, guys? Okay. Perfect. Thank you. Thanks for the confirmation. All right. So before the break, we saw how the architecture of a RNN works, right? Fundamentally, what we saw is we now have to learn these three matrices. We have WHH, WHX, and WHY. These three matrices is what we have to learn. Now, let us see how to do forward and backward propagation using this architecture, right? So let's do a further deep dive over here. So what is being learned here is WHX, WHH, WHY, okay? And let us take an example, okay? So how many people here are tennis fans? Any tennis fans in the audience? No? Okay. No tennis fans? Okay, okay. So let me give you one idea about what I'm going to talk about. There is this guy called Roger Federer, who is a very famous tennis player. Recently, he retired. Okay, he recently retired, and basically, he retired after a very, very good career. So he has something like 20 Grand Slams, which is kind of a rare event in tennis. So Federer joins all-time greats is probably an article which was written after he won his 20th Grand Slam. Okay, so in tennis, it's actually a big achievement if you win these worldwide competitions called Grand Slams. They happen in these select locations worldwide, and if you win one of them, you're a very good tennis player. If you win 20 of them in your lifetime, you're a great tennis player, like one of the greats, right? So okay, just wanted to give that context. The example that we're going to use here for the forward pass is Federer joins all-time greats. That one. Yeah, Indradeep, I absolutely agree. Nadal and Djokovic are probably going to outshine him, but he is a great in his own right, right? Because he's won against both of them also. He's been beaten also, but okay, whatever. Let's come back to yeah. let's come back to RNNs, guys. Sorry for the small digression. Just wanted to give some heads up about this sentence. Okay. So now I have this sentence which I'm feeding into my architecture. How many hidden states? One, two, three, four, five. Uh, five words are there. So five hidden states, right? Okay. So let us analyze this now. This is my X1, which is the word Federer. Okay. This word Federer, I'm going to take as a one hot encoded label. Not one hot encoded label. Sorry. I'm going to I'm going to take this as a one hot encoded label. I'm going to pass it through this word to vec layer, right? Word to vec takes one hot encoded labels only as input. So I'm going to pass it through this word to vec. So this embed over here is the word to vec, okay? Then it's passing through this. And for simplicity now, I have defined WHX to be U, WHY to be V, and WHH to be W. Okay, this is for simplicity. So then I'm going to take this embedded vector, multiply it with U. I'm going to take this hidden state, fixed hidden state, right? This is our first word. So this hidden state is going to be fixed. So I'm going to take this, I'm going to multiply it with W. The sum of these two is going to go to this tan H. Once this output comes, I'm going to multiply it with V to give this output. And I'm going to pass the this as it is to the next one, right? This now becomes my first generated hidden state, okay? This becomes my first generated hidden state. So once I have this, this hidden state now will feed to the next iteration, okay? So what I want you guys to notice here is this W, U, and V matrix are not changing as I'm unfolding this. Okay. This process of repeating this architecture multiple times is known as unfolding. The main thing I want you guys to notice here is I am not I'm not going to change this W, U, and V matrix at all. Okay. This ht minus 4, this hidden state goes feeds into this joins comes here. Then with these two inputs, it's going to give me zy2 and ht minus 3. Now this ht minus 3 and x3 goes in. It gives me y3 and ht minus 2. Okay. And so on and so forth till the last layer. Okay. Now for our problem, since we're doing multi-class classification, what was the type of architecture we had decided? Can you guys quickly remind me what was the type of RNN we were going to display? Many to one, right? So do I really need to care about these over here? ZY1, ZY2, ZY3, ZY4. Do I have to care about them for this architecture? I don't, right? I don't have to care. So this is how we adjust the type of the architecture, okay? When I'm applying this RNN architecture for this current task, which is to give me multi-class classification label, I am going to not even generate these. Okay. I'm not even going to bother generate these. Why bother generating if I'm not going to use it, right? It is actually computationally efficient if I don't even do this matrix multiplication with B. Okay. So remember this. We can optimize this RNN by forgetting to generate this. Okay. Cool. Now let us do a little bit of math to see how the forward propagation is working. Okay. So see here. ZH1 is this guy. How is this coming? I'm taking x1 multiplying it with u, I'm taking ht minus 5 multiplying it with w, and I'm adding a bias term, right? This is kind of important. We are adding this bias term. This bias term is going to be the sum of the bias with this dense layer and this dense layer. Okay. I don't want you guys to be confused. This BH that I have written here is actually the sum of the two biases of u and w. Okay. They're the sum of the biases. Okay. Then I have this h1. How is h1 coming? H1 is coming by doing tan h of this ZH1, right? All I'm doing is tan h of ZH1. That is how this H1 is coming here. So there is a slight problem in the notation here. This shouldn't have been T minus 5. This should have been HT0. This should have been H0 and this is H1. Okay. So guys, imagine that this is H1 and understand this diagram. Okay. Cool. So H1 is nothing but sigma. Guys, is this readable or should I zoom in? Is the math readable or should I zoom in? Okay, I think I should zoom in. Let me try zooming in a bit. Yeah, I'll zoom in. Okay, cool. Okay, is it now visible? This math over here, guys? Okay, perfect. So quick reminder: ZH1, which is this over here, is U times this X, W times this H, plus the biases of both of them. H1 is nothing but tan H of this ZH1. Okay, ZY1, the output over here is V times HT minus 4. This is not HT minus 4 again. This is H1 plus BY, right? Why BY? Because it's the bias associated with this dense layer. Okay, but I'm not going to calculate this for my application. We are not going to calculate this for our application right now. Okay, please remember that. We are not going to do this. We're only going to calculate it for the last layer. Okay. For the last one over here, OT plus 4, this output is where we are going to do this, right? This is what we're going to do. Now, of course, before I give the output, I have to apply something here, right? For multi-class classification, what is the activation? What's the activation for multi-class classification? Softmax, right? Softmax. So softmax is what I will apply here to Z Wi-Fi before I get my OT. So that is the small distinction here. Once I calculate Z Wi-Fi, I have to pass this Z Wi-Fi, which is the output over here, through a softmax layer and then get my final output. Okay. Okay. So if I'm using softmax, what should my loss function be, guys? If I'm using softmax? Categorical cross entropy loss. That's clear to everyone, right? Clear to everyone. Cool. So I hope now the architecture and how we're feeding data is clear. Now let us discuss the main part of this. How to do back propagation with this RNN. And this is kind of complicated, so please stay with me. Okay. This is kind of complicated, so please pay attention here. We are now going to learn how to do back propagation with an RNN. All right, cool. Okay, so let's learn this. The main idea that you have to see here is whenever I'm doing back propagation from here, right? The first step in back propagation is obviously going to be the gradient of this loss function, the CCE, the categorical cross entropy loss function. I'm going to take the gradient of this loss with respect to this V matrix, right? Because I want to update V matrix. So I will take the gradient with respect to this V matrix, and whatever comes here, I'm going to back propagate it to this U that is coming here and this W which is going there, right? So this is the first step of back propagation. Very normal, nothing new over here. Okay, nothing new over here. The new part comes from this point onwards. Okay, guys, the new part comes from here. Now this is interesting. We are back propagating the gradients of this loss function with respect to W over here, right? The back propagation is happening with respect to W. Okay. Is it happening with respect to U or V? Is the back propagation of U and V going backwards through this layer? What do you guys think? Yes or no? No, right? It's not. So you're right. You're absolutely correct. We are not going to bother about this U and V's gradients when we're doing back propagation. We're only going to send back the back prop with respect to this W, because the only connection between this whole architecture and the previous architecture is this hidden state, right? That's the only connection there. That is why we only have to care about backpropagating this W thing. So now let's see how we're doing that. So once again, so over here, guys, if I'm not even computing the loss function, should I have some gradients from this? Should I have some gradients from this? No, of course not, right? I'm not even using this. So no concept of loss function from here. So what I'm going to do is I'm going to again ignore the gradient with respect to this V matrix here. I'm going to simply take this, and this backpropagated gradient is now going to pass to the update equations of this U matrix and this W matrix. Okay, so this W's backpropagation is going to feed into this U and this W. The interesting thing to note here is now I have two different gradients of this loss function with respect to this W. One gradient is coming from this layer, one gradient is coming from this layer. I have two different gradients. How do you think we should solve this problem? I have two different gradient estimates. What should I do here? Is it okay if I just add them? Is it okay if I just add them? Yes, I just have to add them, right? I simply have to add them. Why? Because of how calculus works. Calculus tells us when you have a loss function and you have two matrix multiplications with two separate variables, you will have the gradient with respect to this also, you'll have the gradient with respect to that also. So the gradient with respect to this and the gradient with respect to this are added together before we update W. Okay. And this is the next important thing, guys. Qualitatively speaking, we should not update the gradient here after we have calculated it here. We should wait till the gradient of this, the gradient of this, the gradient of this, gradient of this, and the gradient of this. All those gradients we have to sort of accumulate together and then only update this W. And this is very important. This is the most important thing when it comes to backpropagation through time. Okay, that is why this is known as backpropagation through time, because now you're having different gradients from different time steps. So the strategy to solve this problem is to accumulate all the gradients with respect to these W's at each of these layers, wait till you have all of them, then add them up and then do backpropagation. Okay, we will see this now in detail. Okay, so have you guys understood qualitatively how this gradient is happening? Okay. Oh, Deepith saying did not understand why to accumulate. Deepith, let's see, right? Let the math tell us. Let the math tell us. Let us do this. Okay. So let's do it through math. So okay. So by the way, guys, this diagram is simply showing you what I discussed at the beginning, right? Gradient with respect to V is only with respect to this time step. Gradient with respect to W is depending on all time steps. Gradient with respect to U is also depending on all time steps, but not for our problem. If I was using these, then I would have to update V with respect to all, right? No, my bad. U is also going to depend on all of them, right? Because W's gradient is backpropagating here. So U and W both are going to require all the gradients from our hidden steps. Okay, all the gradients from our hidden steps for these two matrices, but for V, only one thing is there. Okay, cool. Now let us see the math and let us try and understand this. Okay, first we'll see the math for this very simple step. Okay, for this very simple updation of V matrix, let us see the math. So basically, how do I update V matrix? I need gradient of this loss function with respect to this V matrix, right? How am I calculating that? I'm first calculating the gradient of this loss function with respect to O of t. Then I'm calculating the gradient of O of t with respect to Z of t. Then I'm calculating the gradient of Z of t with respect to V, right? Let us understand this very carefully. So let me take this equation. Let me paste it over here and let us understand in this context. Okay, cool. So see this. Finally, what we want to do, we want to update this V matrix, right? So let me just call this V matrix over here. Okay, for simplicity, this is V. So to update this V matrix, I first have to take this output, right? I have to calculate the gradient of the loss with respect to gradient of the output. Okay, OT. This is this term. Then what I have to do is I have to calculate the gradient of this output of t with respect to this input that I'm giving it, right? This, remember that this is ZT, whatever is coming from here is ZT. So gradient of this output with respect to ZT is what I have to calculate next. And then the gradient of this ZT with respect to V matrix, right? V matrix. So this ZT is multiplying this V matrix and then it's going. So this is what I'm going to do finally. And that is how I get this final gradient of this loss function with respect to V of t. Standard stuff, nothing new here, right? Everyone with me so far? Everyone with me so far? Yes or no? Okay. 2 people are with me. I'm happy. I hope the others are as well. Let's proceed. Okay, cool. So now all I have to do to update this V is V is equal to V minus alpha times LT by dou V, right? Standard gradient descent step. Okay, let's move on now. Now let's see how to optimize with respect to W. Okay, so optimization with respect to W now again is kind of complicated because we don't only have to take the gradient with respect to this output, we have to take this also, this also, this also, this also. So now let us try and understand how this is working. Okay, so we have to now understand these set of loss functions. Okay, so gradient of the loss with respect to W at different time steps are going to be as follows. Okay, so first of all, we're going to forget about the loss function. We're only going to worry about gradient of this W with respect to the hidden state for this thing. Okay, so now whenever I'm going to calculate the gradient of W, for this gradient I'm going to compute it with respect to this output. For this one I'm going to compute it with respect to this hidden state. For this one, this hidden state, this one, this hidden state, and this one, this hidden state. Okay, now let's see how that looks like. So gradient of hidden state T with respect to W is gradient of hidden state T with respect to W plus dou H by dou H T minus 1 into dou H T minus 1 by dou W, right? This is standard chain rule. This is standard chain rule. I'm going to first do it with respect to T minus 1, then I'm going to do it with respect to this. And notice this, this is the accumulator. Remember I told you that we have to accumulate this. This is happening because of the chain rule, right? This is happening because of the chain rule. So over here, when I'm calculating the gradient of this W with respect to HT, right? With respect to HT minus 1, when I want to get the gradient of this W with respect to HT minus 1, I have to first do it with this HT and then multiply it with this locally, right? That is what I have to do. And that is how I'm getting this equation here. The same pattern applies. So HT minus 1 with respect to W is going to be dou HT minus 1 by dou W plus dou HT minus 1 by dou HT minus 2 into dou HT minus 2 by dou W. Okay. This pattern now follows everywhere. Okay. Once we now bring all of this together, right, it becomes the following. LT with respect to dou W is LT with respect to dou OT into dou OT by dou ZT, right? Which is nothing but dou ZT by dou HT, which is basically, Yeah, no. Notice that this term is multiplying this one. Okay, this is multiplying this. So we have dou LT by dou OT into dou OT by dou ZT into dou ZT by dou HT, the whole into this thing. Dou HT by dou W plus dou HT by dou HT minus 1 into the next equation. So all I'm doing here is I'm substituting this backwards. Okay. So wherever this term is there, I'm putting this whole thing. So the innermost equation is this yellow one. Then when I substitute this yellow part to this orange part, the remaining one is over here. Then when I substitute this orange part for the green part, the remaining part is over here. Then when I substitute this over here and so on, right? So this is how we are getting this. Okay. So Anil's question is didn't get the plus thing. Okay. Let me explain this slightly better. Okay. Let's come back here. Let's work with this. Right. Okay. Okay. So let's focus on this part. Right. Okay. So what I want you guys to notice here is this. This is a neural network. So there is some cascading happening. Okay. Let's understand where that cascading step is happening. Whatever I have here is my output, right? So first I'm going to compute dou OT plus 4 by dou, sorry, my bad. I'm going to compute the gradient of the loss with respect to this, right? Okay. So the first thing I'm going to calculate is gradient of the loss with respect to this OT, okay? That is what I'm calculating here, okay? Then when I want the gradient of this with respect to W, right? What is it that I have to do? What is it that I have to do? Let us see, okay? Once I have this OT over here, where is W appearing first time over here? W is appearing for the first time in this part, right? If you notice, W is appearing for the first time here. So now what I want to do is I want to now calculate the gradient. To calculate gradient of loss with respect to W, I have to first calculate the gradient of the loss with respect to OT, then multiply that by gradient of the loss with respect to gradient of OT with respect to this ZH5, and then multiply this by the gradient of the loss. So loss with respect to OT, OT with respect to ZH5, and then ZH5 with respect to W, right? Do you guys see this part? Is this part clear to everyone? Anil and Deepit, this is clear, right? How I'm getting this equation? Okay, cool. Now let's see what happens the next time I have to get here. Okay. Now let us see next time when W is coming. Next time over here, W is coming in this equation, right? If you notice, next time W is coming in this equation. So now let us build the strategy to calculate loss with respect to W the second time. Okay. So now gradient of the loss with respect to W for the second time is going to be nothing but gradient of the loss with respect to this ZH4 into gradient of the loss, gradient of ZH4 with respect to W, right? Now to understand how that plus is coming there, okay, we have to retrace our steps of this part. So we have to expand this part now. This part is kind of obvious. This part is what we have to expand. So what I want you guys to see here is the ZH4, right? ZH4 is X4 times U plus HT minus 2 times W plus BH, right? From this part, where is W coming over here? It's coming through this HT minus 1, right? So HT minus 1 is nothing but H4 over here, right? So this is nothing but sigma of this. So now if I bring this ZH5 and substitute it in this sigma, you will see that we have sigma of this whole thing, right? We have sigma of that whole thing. So now I want you to understand that when I'm taking the derivative of H4 with respect to W, I have the following equation, okay? Let us expand this to understand it better, okay? So my ZH4 is X4 times U plus HT minus 2 times W plus BH, okay? What do I have to substitute here? Now I have to substitute HT minus 2 here, right? So this is how I'm going to expand it. So now I'm going to substitute HT minus 2 as this, right? Sigma of ZH5. This is X5 into U plus HT minus 1 into W plus BH, right? It is sigma of this whole thing, okay? Cool. Now this whole thing is now multiplying this W, right? So now do you guys understand that if I apply chain rule here, I'm going to have one gradient with respect to this W and I'll have to add it to the gradient of it with respect to this W. Are you guys able to see this through chain rule? Are you guys able to see how this recursion is causing that plus to come there? This is because of that recursion we're doing, guys. When we take this and we substitute it back here, because of chain rule, it sort of puts an additive term there. And that is why we get this kind of a thing. Okay. So that is how we are getting this addition part. Is the addition doubt clear to everyone? Addition doubt clear? Cool. Awesome. So let's move on. So now let us kind of see how this is going to work. Okay. If I now keep doing this, right? If I keep doing this and I rearrange these terms, okay. Remember guys, there are three terms over here which are multiplying everything inside these brackets. Okay. Now I'm going to apply the multiplication on these brackets and I'm going to open the whole thing up. Okay. Once I apply multiplication and open the whole thing up, this is what I'm going to get. Okay. This is what I'm going to get. So if I had to generalize this whole thing into a single formula, I can do this part. And then finally, the update equation for my W is going to be W minus alpha times dou LT by dou W. Okay. This is how I'm going to get my whole thing. Okay. Cool. Okay, guys, you remember the sigma was tan H? You remember this? Sigma is tan H. Can you now tell me what's the problem here? What's the problem? Vanishing gradients, right? Okay, vanishing gradient. Any specific observation? Any specific observation? Do you guys see that contextual information is getting lesser and lesser gradient weights as we're moving backwards? Are you guys noticing that this contextual weights are getting lesser and lesser importance as we're moving backwards because of vanishing gradients? See, the gradient for this last step, the gradient for this last step is very low and the gradient for the first step is very high, right? Okay. This causes two problems for us. Okay, two problems. First problem is at a implementation level. The implementation level problem here is we will have vanishing gradients. So this network is going to be very tough to train. Very tough to train. The solution to this is very simple. Replace tan H with something else. But people saw that replacing tan H with something else causes a different problem. What will that problem be called? Guys, imagine if I replace tan H with something else and these are all very large numbers. What problem does that cause? Exploding gradients, right? Yes, yes. So this is the issue here. If we use tan H, we'll have vanishing gradients. If we replace tan H with something like ReLU, we may get exploding gradients for very long sentences. Okay. That is why, for this reason, exploding gradients and vanishing gradients problem, RNNs are very, very difficult to train. Okay. There are certain strategies. So there is this guy called Andre Karpathy who figured out a strategy and he said, no, they're not difficult to train. It's the opposite. So I want you guys to read this blog. Okay. The unreasonable effectiveness of RNNs. Yeah. So I'll just want to paste this over here. This guy says, I figured out a strategy to train these RNNs and saw that they were actually easier to train. So just go through this article. You will see how to train an RNN. Okay, cool. But coming back, this is the first problem with it. The second problem is at a conceptual level. Words that I have seen far back have lesser importance now than words that I'm seeing later on, right? So what do you think? So if you had to account this with some sort of mental health problem, yeah, context is getting lost when we have long sentences. We are not effectively storing context information when we have long sentences, right? So if you had to say this is a problem with someone's mental health, what is the term you would use? Can we say that this is like short-term memory loss? Can we say this is like short-term memory loss? Okay. This is something we have to remember. Next class, we're going to discuss how to solve this problem of short-term memory loss. We're going to specifically see how to design an architecture so that we now have long short-term memory, right? That is how the name is coming. Long short-term memory. So LSTM name comes from there. Okay. So we're going to fix this problem later on. Just wanted to pause here, explain these two problems to you. Okay, cool. So the update of this U matrix is also straightforward. I don't want to go into depth here. It's kind of straightforward, guys. Whatever we did for W, same thing. This thing. So old joke Ghajni. Yes, exactly. This is the Ghajni problem. And go to neurosurgeon is the solution, or you can go to a neural network architect. Both will solve this problem. So yeah. Anyway, sorry. Coming back. Let's come back. I just want you guys to go through this derivation of this U matrix. Basically, it follows the same steps. Please just go through this, okay? Okay, cool. Before we move forward, I just wanted to show you what would happen in the multi-output problem, right? What is the major change that would happen to this architecture if I started taking all these outputs into consideration? What is the major change, guys? Will the update equation of V remain the same? We will have a loss at every t, and our final loss function is the sum of all these loss functions. So now V was very easy to update for our current problem, right? But for that problem, we will be kind of difficult to update. Okay, we will be difficult to update. We will no longer have this kind of easy thing. So if we switch this to a multi-output problem, right? So multiple input, multiple output, if we switch to that, we are now going to have to update V also using the sum of these things, Okay, cool. So that's the idea here. Now, can we use the information from the future as well? So what we have done so far, guys, is we have shown one full sentence and then we're asking it to do something, right? But if we wanted to modify this architecture to do something like fill in the blanks, we will have to not only provide the starting letters, we have to also provide the ending letters, right? So it is possible to do this using something which is known as bidirectional RNN. How this works is basically whatever hidden state I was passing on, right? I will also send that hidden state backwards. So now I'm going to have an architecture which is going to have multiple hidden states, right? So if we now design the architecture this way, we can sort of end up with this. Bidirectional RNNs are actually, to the best of my knowledge, not that widely applicable for the kinds of tasks we generally train them for. So it's optional for you. So fill in the blank type tasks aren't really that complicated, right? So generally we would look for other solutions to architectures. So yeah, I kind of request you to go through this maybe offline. Just kind of see how these things are flowing around, right? Just kind of check how these things are flowing around, and then we can basically come to this bidirectional this RNN. Okay, cool. So now that we have discussed all of this, okay, guys, sorry. One major thing. When it comes to bidirectional this thing, right? When it comes to bidirectional RNNs, it's important to remember that we will now have two separate WUVs. So we will have one WUV for the forward direction. We'll have one WUV for the backward direction. So that is kind of important to remember. So it's like you have now two RNNs which are talking to each other. One guy is encoding things which is coming from the past. One guy is encoding things which is coming from the future. Now both of these are then feeding into this guy, and it is predicting the word. Okay. So this architecture kind of just go through it offline. I'll leave it to you to see this. And for the next 10 minutes, if it's okay with you guys, let us discuss the implementation of this. Are you guys okay if I take a 10-minute extra today? Like just 10 minutes? That is enough to sort of see the architecture. Luckily for us, 1 minute, huh? Luckily for us, Keras actually makes this very easy. So the entire RNN, right, is basically encoded into this single simple RNN layer. Okay. So let me show you this syntax. So, and also I will pin this for you. Okay. So whatever we're going to discuss next class we're going to see LSTMs, and after LSTMs we might discuss GRUs, right? Gated recurrent units. So for this, I'll just want to paste this link for you guys. If you have time, just go through this. Keras code for implementing these are very simple. Okay. And you can get the summary of it here. Today, I want to focus on this simple RNN layer. Okay. Cool. Amit says peephole GRU variant is also required. Yeah. So GRU is this thing, right? Are we going to discuss this? I'm not sure. I'll just get back to you. Maybe we'll wait for that class. I'll take this doubt up then, right? For now, let's focus here. We have simple RNN. This simple RNN layer takes care of all three matrices. Okay, guys. Internally, it has this V matrix, this W matrix, and this U matrix. You don't have to separately define it using layers and everything. So it is enough if you just know how to use this one function to implement the whole RNN. So that is why the implementation of this RNN is very, very simple. We simply have to do this. From tensorflow.keras.layers, import simple RNN. That's all we need. Okay. This other stuff is not required for today. So let me just get rid of it. All this other stuff is not required. Okay. The layers that we're going to require today are this input layer, this embedding, this dense, and this simple RNN. These are all we need to implement whatever we have learned today. Okay. So let's go through this quickly. All of this is, the rest of the imports are not very important. They're just the usual imports, like the ones for pre-processing, the ones for other stuff. So it's okay if we kind of skip this. Talking about this, moving on. This is just a function which does data cleaning, the usual thing, right? First, make everything lowercase, remove all the full stops, the exclamation marks, all that, right? Then remove stop words, then remove punctuations, join the words back to form tokens. So basically tokenization. Remember, it's important to keep the order here. And whatever we've done here is making sure that the order of these words is maintained. Okay. And finally, we have this cleaned word, cleaned sentence, and that is what we're going to use for training. Okay, cool. So this cell is basically just applying this cleaning function to all our input titles. Okay, remember, we're only going to focus on the titles. So this code block is only going to take care of the title part, right? Okay. Now we're kind of fixing the sequence length. Yeah. So let's kind of see what is the maximum length over here. So the median length seems to be somewhere around 5. The median seems to be around 5. We have kind of two outliers. One is 2 length and the other is 7 length. And we can set the sequence length to be the max words in the longest sentence, right? Cool. So just one moment. I kind of want to understand why we're doing this. Max sentence length is this, strip this, total classes is n unique. Maximum sequence length is this, total classes is 5. Okay. Let me see if we're going to use this. I don't think we're going to use this anywhere. Yeah, we're not using this really. That is just to sort of see what is the sequence length. It doesn't really matter when we're passing it through our network. Okay, cool. So here, we're doing the train test split. Here we're doing the reset index. This is basically to speed stuff up, right? Yeah, this is to speed stuff up. Then here we're displaying the train test data sizes. We have the one hot encoded versions of these labels. This is basically, okay. So guys, in this specific example, right, I'm choosing to, so let's go back to this slide, right? I told you that there are three ways to do this. One hot encoded word, fixed word to vec, trained word to vec. So in this example, I don't want to take the pain of transfer learning. So what I'm going to do is I'm simply going to introduce this layer called the embedding layer. Okay. So there is something which is known as embedding layer. All this embedding layer is doing is it is taking the sparse indices from that one hot encoding. So the input to this embedding layer is the index from that one hot encoded label. Okay. And what it will give you is the final embedding that you want. So over here, if we wanted the vector representation of size 100, I'm basically telling it, you learn from scratch. I'm giving this network freedom to learn the embedding from scratch for my words. Okay. So generally, if we try to do transfer learning, right, it would be better. But for this example, we're going to keep things simple. We're not going to do that. Okay, cool. So that is why I have this embedding layer over here. Now let's see. So tokenize and pad, this is basically going to just do the whole thing, all of that. Then we have choose the latent dimension and embedding dimension. So this is our UWV. Our latent dimension, so the latent dimension that they're talking about here is basically this, the dimension of this hidden layer. Okay, that is the latent dimension. Embedding dimension is the length of this vector representation. So we are setting the embedding length to 100. We're setting our hidden layers dimensions to 50. Okay, for this example. Okay. Now this is where we are actually defining our RNN. It's very simple. It's a sequential model of embedding followed by the simple RNN, followed by dense, followed by model summary. Okay, this is what it is. Simply, it is a sequential of embedding, simple RNN, dense, and that's all. So we don't have to apply any extra logic to implement the simple RNN. Using this function is enough. Okay, cool. So now let us go ahead and train this whole thing. All right, let's go ahead and train this whole thing. So now we're going to conduct our training over here. Training as usual in Keras is model.compile followed by model.fit. Nothing new here. Okay, nothing new here. We're going to train this for 10 epochs and let us see what we get after 10 epochs. So let's quickly see how this proceeded. Okay, so this is what my epoch versus accuracy plot looks like, right? So it looks like my training accuracy as a function of epochs increased, but my validation accuracy kind of saturated. What kind of problem is this when we're training neural networks? Overfitting or underfitting? Overfit, right? This is an overfitting problem. So we have to think of ways to deal with this problem if we're practically doing it. Okay. Just remember, it's important to keep these concepts in mind, not forget that. We have to see how to modify our architecture or training strategy so that this becomes closer to that. So maybe that is something you can sort of take up after you read this article. Okay, there are some strategies this guy discusses which are very nice. So please just go through this if possible, and you can try strategies from there here. Let's see how the loss proceeds. Right, loss also shows the overfitting problem. Okay, the training loss is much lower than the validation loss, and it looks like we need early stopping here. Right, it looks like we need early stopping here. The final output that we're getting is not the best one in terms of validation. So if I was doing this, I would have used this as my model. Okay, this seems to be the lowest one here. Let's see, what is the validation accuracy here? It's 0.8343. So guys, notice this number which comes here. Okay, at 6, it's 0.8343. Smooth value. Oh, sorry, I have to look at the value, right? So the loss is higher here, the loss is lower here, right? So I would have used this epoch to evaluate my model, but unfortunately we're not going to do that. We have not added any callbacks, right? We have not added any callbacks. Oh no, we have added an early stopping callback. Okay, cool. Sorry, my bad. We have done this. So whatever we're going to see is going to be the result of this one. Okay, we're going to see the result of this model, 6th model. So now this is where we are saving the model. This is where we are loading it. And now let us make predictions on the test set. So guys, remember this is the validation set. Now we're doing it on the test set. Okay. The test set accuracy turned out to be 0.77%. And this seems pretty decent to me for this kind of a task. So we now have a test set accuracy of 0.77. We know what we have to do if we want to improve this. All the strategies we've learned from our neural networks classes to sort of bridge this gap that we have to apply. We'll be seeing some more strategies for LSTMs next class. They're kind of similar. So let's discuss it then. And yeah, let's finally see the confusion matrix. Okay. So let us, by looking at this, can you tell me what is it confusing the most for what? So 0, it looks like is being confused a lot for 3. So let's see if there is any relationship between 0 and 3 in our labels. So what was 0, what was 3? Let's see. So 0 was sport, 3 is tech. For some reason, it is confusing tech and sport a lot. Okay. Maybe there are some articles about sports analytics, who knows? So yeah. So this is one place where it's confusing a lot. It's also confusing 2 and 3, right? 2 and 3 is getting confused a lot. So we could probably see what's the relationship between those two categories. Let's quickly check that. 2 and 3, politics and tech. Okay, that was kind of unexpected, but fine. It's confusing those two. Okay, but at the end of the day, this is where we are with the RNN implementation for this application. Yeah, tech is confusing with everyone. Yeah, it looks like tech is the one it is most vague about. Okay, tech people are everywhere. That's my takeaway from this. So yeah, anyway, cool. So finally, let's end this. Yeah, tech is everywhere, right? Let's end this lecture by looking at a few things to keep in mind. RNN takes the current input at time t as well as hidden state from the previous one. This hidden state is nothing but the memory, okay, in our network now. There are 3 weight matrices, W, U, V. And for bidirectional, we're going to have 6 matrices. Just kind of remember that. If we're switching to bidirectional, we'll have 6 matrices. Bidirectional processes information from left to right as well as right to left. Same RNN unit is used for all the inputs so that weight is shared across. Gradients are calculated over time, which is done through backpropagation through time. So this BPPT is backpropagation through time. And if you guys want the paper, right, where this first came, the paper's link is attached here. So this is Verbose. He basically was the guy who proposed this back in 1990. Okay, he proposed this backpropagation through time in 1990, and that is what we're still using today. Okay, same idea is going to be used for LSTMs and eventually for our transformers. No, it's just attention, right? It's not recurrent. Okay, no, not for transformers, for LSTMs. Same thing is going to be used. Yeah, cool. So that ends the lecture for today. I'm going to now start the doubt session. Those of you who have any doubts with respect to today's lecture, please stay back. Otherwise, you can leave. Thank you for your attention, guys. Let me solve the first doubt which was asked in the questions tab. Okay. So first, let me take Anil's question. I can answer that really fast. Is RNN related to ResNet? No, it's not. It's not really related to ResNet. In ResNet, the residual connection is between the inputs itself, right? Here, we have a variable length. So the objective of the hidden state here is to handle variable length and to store some information from the previous words so that it can take it later, right? Residual informations, the residual skip connections job is to get rid of non-useful units. So there are two very different purposes. So it's not exactly related. No, they've two separate jobs. Cool. The next question is by Arun. Hey Arun, can you please tell me the question number and the name of the lecture? I guess it's last lecture only. Can you please tell me the title of the question? I'll just bring it up here and let's discuss it, right? Just 1 minute. On my side, I'm opening the assignment. Not getting it. Okay. This is, yeah, okay. So this is topic modeling class. Gibbs probability. Yeah. I'll just check the assignments. I just need to understand what is Gibbs probability. Is it a distribution or is it some this thing? It's just a notational thing, guys. I'm pretty sure we've covered the concept, but we have not covered the yeah. So just 1 minute. Topic modeling definition, LDA hypothesis, word cloud to pos functions, LDA multinomial distribution. I think it's this one, right? Is the title of the question LDA multinomial distributions? LDA sampling. Okay, 1 minute. I'll quickly do that. LDA sampling. Okay. LDA starts with random assignment of topic to each word and iteratively improves the assignment of topic to word through dash, right? Stratified sampling, Gibbs sampling, cluster sampling, direct sampling. So, okay. So this has to do with the sampling strategy. Okay, fine. It doesn't have to do with the Gibbs distribution. Gibbs sampling, let's see. Let's understand this. Okay, guys, I'm really sorry. This is a detail even I was not aware of about LDA. I'll quickly see what makes sense the most here. Let us figure this out. Let's figure the answer to this question out. First, let's understand what's Gibbs sampling. This is the correct answer, right? Let's see what this is. Gibbs sampling is commonly used as a means of statistical inference, especially Bayesian inference. It is a randomized algorithm that makes use of random numbers and is alternative to deterministic algorithms for statistical inference, such as BLA, right? Okay, so let me understand this first. The samples approximate the joint distribution of all variables, right? Cool. Okay, awesome. So this property, I believe, is what's most important right now. So guys, from last class, if you remember, right, in LDA, if you remember our discussion in LDA, yeah, so LDA sampling, we need to minimize the error like for topic documents. Yes, Arun, that is the application. But if you remember, the last classes when I was discussing the sampling part, right, I told you that the way we sample this is if I have this 3 topics, right? Imagine this is the triangle for those 3 topics. Let us say I have set the number of topics to 10. Then for a single document that I'm giving, okay, what it's going to do is it is going to create a probability distribution here, okay? It is going to create a probability distribution for this one. If you remember, the distribution used here is the Dirichlet distribution. And then we have to now generate a matrix such that it is being generated by this distribution, right? So the property which is required for us when we are sampling is the samples have to approximate the joint distribution of the variables. The joint distribution of the variables is the joint distribution of the topics that we have learned, right? So because of this one property of Gibbs, it is the correct sampling technique to apply here. Let us now go and check the other ones and let's by elimination figure out if the other sampling techniques won't work here. Okay, let's do that. So let's see stratified sampling now. Let's see stratified sampling. I believe stratified sampling is hierarchical of some sort, right? Researchers divide subjects into subgroups and based on characteristics they share, right? So if I had to apply stratified sampling to my current problem, I would have to sample separately for this, separately for this, and separately for this. But this will be wrong, right? Because what we want this matrix to, what we want this matrix to represent is the joint probability distribution that we are learning. So stratified sampling would have been the wrong answer here, right? So that is why stratified sampling won't work. Okay, let's see the next one. The next option is cluster sampling and direct sampling. So first let's do direct sampling. So direct sampling is somewhat informal term when the sample is taken from the actual population and not from some kind of this thing, not from some kind of distribution, right? There is no option of direct sampling for our current problem. There's no option of direct sampling. Why not? Because we don't have a population. What we have learned over here in LDA is a distribution. So we have to use the distribution somehow. That is why by process of elimination, we cannot apply direct sampling here. And finally, let's eliminate the last one, which is cluster sampling. right? This is cluster sampling. Let's go here and see. So in cluster sampling, a probability sampling method in which you divide a population into clusters, such as district and schools, and then randomly select. So clustered sampling and stratified sampling seem similar to me actually, right? They seem similar. Are they the same? No, they're not. They're not. My bad. Clusters. So stratified. Yeah, they're not. Sorry, they're not. The difference, as I understand it, is in stratified sampling, the sum has to be your this thing. So the joint probability has to be there. Whereas in clustered sampling, I separately sample from each of them, right? I separately sample from each of them, and there's no guarantee that this will correspond to my final probability distribution. That is what that is how I'm understanding it. Let's see. I'll check this 1 minute. Divide a population into clusters, then randomly select some of these clusters as a sample. So that's what, right? In cluster sampling, there's no guarantee that the sample that you have follows the joint distribution. So again, cluster sampling isn't the right option here. So the correct answer by process of elimination at least is Gibbs sampling. Why? Because the sample approximate the joint distribution of all variables. This is the property we wanted. So this is the correct answer. Cool? Does that answer your question, Arun? Awesome. I'll mark this as answered. If anyone has any further doubts, I'll stay back for a couple of minutes. Yeah, Indradeep, I actually discussed this at the beginning of the class. Flipit project, there is a technical bug on our side, okay? There is an issue with the dataset and the evaluation notebook. So when we run checks, there is some issue with the answer that we have given and the check that is there. So because of that, they have temporarily just redirected it to the post street. That will get fixed when we fix that bug. Just give us a few days, okay? Our team is fixing it. So the evaluation criteria and this thing is, yeah, it's okay. Really sorry about that. This is a technical bug. We'll fix it. And it's all right, man. It's perfectly fine. As long as you didn't miss anything important, that's good, right? Cool. Okay, guys. So if we're done, I'll end this lecture here today. Thank you so much for your attention. Guys, I really recommend you join the next few lectures, right? Because now we're slowly building our way towards GPT-like architectures. So and we have this module which we're designing, which will sort of give you access to large language models and knowledge like that. Okay. So we're mostly going to launch that on 17th or 18th of May. So if you guys are interested, you can sign up for that. And we'll give you the option if we are on time with the scripts and everything. To understand that, the next few lectures are going to be important. So kindly request you to pay attention for the next few lectures. It will prepare you to understand things like ChatGPT and Auto GPT and stuff like that. So yeah. Anyway, thank you so much for being an amazing audience. Am I audible to you guys? Hello? Hey guys, sorry, there's been a no. I'm really sorry. There's been a power cut on my end. The timing was beautiful actually. So you're not able to. My camera is actually on. So 1 minute, I'll show you. I'm still here. Like, wait. अरे किधर है? हाँ, flashlight. I'm still here. It's just power cut. So sorry about that. Horror film. Yeah, sorry about that. I'm actually ending the class here if you guys don't have doubts. I'll see you next time. I'm ending the lecture. So before I ended the lecture, power cut happened. So sorry. Good night, guys. See you next class.